Hi, welcome to this video where I will describe the results from our paper Distributed Approximation on Power Graphs. I am Shreyas from the University of Iowa, and this is joint work with Reuven Bar-Yehuda, Keren Censor-Hillel, and Yannic from the Technion, and Sriram Pemmaraju from the University of Iowa. A full version of this paper is available on arXiv. The link is at the bottom of the slide. In this paper, we study optimization problems in the congest model. In the congest model, we are given a graph G, which is the communication network. We are in a synchronous message passing model where the nodes can send order log n bit messages per neighbor per round. The central question we want to ask is what makes optimization tasks easy or hard in the congest model. An example optimization problem is minimum vertex cover. In this problem, we want to find the smallest set S of vertices such that at least one endpoint of each edge is in S. Exactly solving GMVC in the congest model requires n squared rounds. And we can get a 2 plus epsilon approximation in roughly order log of the maximum degree rounds. And for approximation factors below 2, the fastest known algorithm is to gather all edges of G at a single vertex and solve the problem locally, which takes order n squared rounds. In this paper though, we look at optimization problems on G squared. We are still in the congest model with communication graph G, but we want to solve the problem on the squared graph G squared. In G squared, we have an edge between two vertices that are at distance at most 2 in G. If we are allowed unbounded messages, like in the local model, then there is no difference between G squared and G. So congestion is the only issue that we can face. Since the communication network is G, congestion can become a significant issue. The nodes may not even be able to learn all their incident edges in G squared quickly. These are the dashed edges shown here. Moreover, the incident dashed edges are not part of the initial knowledge at a node. Rather, their existence must be inferred from the edges in G. So why would we want to study power graph? Vertex coloring of G squared arises in applications like frequency assignment in radio networks. This is because if two neighbors of V use the same frequency, it leads to a collision at V. So we would want two hop neighbors to have different colors. Moreover, de-randomization techniques in the local model rely on computing network decompositions of G squared. Also, studying optimization problems in G squared might give us insights into solving optimization problems in G. When solving optimization problems in G squared, we can face issues due to congestion, but on the other hand, G squared has more structure compared to G, which we can exploit to design faster algorithms. We can exploit structure in G squared as follows. The set of all vertices is a 2 approximate solution for G squared MVC. So this implies a 0 round 2 approximation algorithm for G squared MVC. Whereas for GMVC, we need roughly log n rounds to get even a constant approximation. And this log n term is actually a bit more complicated, shown here. In this paper, we analyze the effect of congestion versus structure on two problems. Minimum vertex cover, which I call G squared MVC, and minimum dominating set, which I call G squared MDS. In general, G squared MVC becomes easier and G squared MDS becomes harder compared to the current status of the two problems on G. The two main distributed results in this paper are a deterministic 1 plus epsilon approximation algorithm for G squared MVC in n over epsilon rounds of the congest model, and an n squared lower bound for any C approximation for C less than 9 over 8 for G squared MDS in the congest model. Prior to our paper, there was no work on G squared MVC. For GMVC, there is an n squared lower bound for exact computation by Censor-Hillel, Khoury, and Paz. And nothing better is known for approximation factors between 1 and 2. But for G squared MVC, we improve the running time from the trivial n squared to n over epsilon rounds. As far as MDS goes, Bachrach et al. Showed that an exact solution for GMDS also requires n squared rounds, and no lower bound is known for approximation. But for G squared MDS, the same paper showed a linear lower bound for log n approximation. But you cannot compare a linear lower bound to a quadratic lower bound. We show a quadratic lower bound for constant approximation, which we can compare with the exact lower bound for GMDS. We also show quadratic lower bounds for exact computations of G squared MVC and G squared MDS in the congest model. These lower bounds, as well as the approximate G squared MDS lower bound, are based on reductions from two-party communication complexity, like in the previous work. At a high level, our lower bounds are obtained by replacing each edge of previous lower bound graph constructions by gadgets which allow us to reduce the solution in G squared to a solution in G. Here is an example of how we replace an edge by a gadget for minimum vertex cover. In this case, we show that the vertices labeled 1 and 2 in the gadget on the right can be added to the minimum vertex cover without loss of generality. Therefore, we can assume that the gadget leaves an uncovered G squared edge between U and B, showed by the dashed edge. In particular, we show that given a graph G, we can create a graph H such that the size of MVC in G is related to the size of MVC in H squared. More formally, the size of MVC in H squared will be the size of MVC in G plus 2 times the number of edges in G. We have a similar reduction for MDS also. The lower bound graphs in the previous work have n squared edges, which means that we will end up having n squared gadget nodes in our lower bound graph. This is a problem since we have an n squared lower bound on a graph with n squared nodes, which means that the quadratic lower bound will become a linear lower bound. To avoid this, we carefully share the gadgets for most edges, which allows us to have only a linear number of gadget vertices, which makes the total number of vertices in the graph linear, and the n squared lower bound holds. These gadgets also allow us to get sequential hardness results, such as NP hardness for both problems, no fully polynomial time approximation scheme for G squared MVC, and no better than log n approximation for G squared MDS. We also show a polynomial time 5 over 3 approximation for G squared MVC. This sequential algorithm is interesting because for GMVC, obtaining a better than 2 approximation is NP hard under the unique games conjecture. And there is a long tradition in graph algorithms for obtaining better than 2 approximations for different families of graphs, like planar graphs, claw-free graphs, graphs with perfect matchings, and so on. we add the family of squared graph also to this list. So let me describe the algorithm in more detail. The algorithm consists of three parts. In each part, we find an approximate solution to the remaining graph from the previous part. In the first part, we keep on adding triangles. That is, while there is a triangle in the remaining graph, we take all three nodes of the triangle to the vertex cover, which we call S1, and we remove these vertices and their incident edges from the graph. Notice that for every triangle that we add, optimal has to add at least two vertices, and we add exactly three vertices. So our solution will be a 3 over 2 approximation. In the second part, now we have a triangle free graph, and we carefully add low degree vertices to the vertex cover, which we call S2. At the end, the minimum degree of the remaining graph is 4. This part is crucial for the analysis, but I won't describe it here in detail. You can take a look at the paper for further details. In the third part, the remaining graph from the previous parts is triangle free and has minimum degree 4. And what we do is we compute a 2 approximate vertex cover in the remaining graph. We call this S3. So to sum up, the results of the three parts are, we get S1, which is a 3 over 2 approximation, S2, which is a 5 over 3 approximation, and S3, which finishes off the vertex cover, is a 2 approximation. Typically, we would take the maximum of these three approximation factors, but in this case, we would get a 2 approximation because of S3, and we don't want that. So what we show is that the size of S3 can be bounded above by 2/3 the size of S1. This allows us to take some vertices from S3 and charge them to the optimal solution of S1. Notice that 3 over 2 is less than 5 over 3 is less than 2. So we are taking nodes from a more expensive solution and charging them to a less expensive solution. So overall, we get a 5 over 3 approximation. For the rest of the talk, I will describe our deterministic 1 plus epsilon approximation algorithm for G squared MVC in the congest model, which takes n over epsilon rounds. Just a quick reminder, the setting is that we are in the congest model with communication graph G, and we want to solve minimum vertex cover on the squared graph G square. Consider a vertex in G with 3 neighbors. The square of this graph is a clique on 4 vertices. So the optimal vertex cover must have size at least 3, and taking all 4 vertices is a 4 over 3 approximation. We can generalize this argument to vertices with degree at least 1 over epsilon. So taking all vertices in the vertex cover is a 1 plus epsilon approximation. This suggests an algorithm where you repeatedly add disjoint stars to the vertex cover. This is the pseudocode for the first attempt. You begin with an empty cover, and while there is a vertex V in G of V minus S with degree at least 1 over epsilon, you add V and its neighbor to the cover. A big problem with this approach is that when we add a star to the cover, a leaf of the star might have large degree in G. This induces a clique of uncovered edges on the red vertices, but since there is a clique, we can safely add these vertices to the cover and still stay within 1 plus epsilon factor of the optimal solution. So this suggests a second attempt where we iteratively add red vertices to the vertex cover and stop when a leaf has less than 1 over epsilon new neighbors. As we are done with a tree, we start growing other trees. So the pseudocode changes as follows, where we grow these trees and add them to the cover. We show that by breaking symmetries by 2-hop ID, we can compute this set S in epsilon n rounds in the congest model. As a result of the second attempt, we partition the vertices as shown in the figure. Since all vertices of S are in the vertex cover, the only edges that are uncovered are those in G squared V minus S. Here is a small example of what the remaining graph can look like. We show that each node of S can induce a clique of size at most 1 over epsilon in G squared V minus S, and each node in V minus S has degree at most 1 over epsilon in G of V minus S. So we can aggregate these G edges at a leader vertex in n over epsilon rounds, which allows us to recreate the remaining graph at the leader. And we can also compute an exact vertex cover of the remaining graph locally at the leader. Note that this local computation may not be polynomial time. Therefore, we have a 1 plus epsilon approximation on one part of the graph and an exact solution on another part of the graph, which together covers all the edges of G squared. Therefore, we can compute a 1 plus epsilon approximation to G squared MVC in epsilon n plus n over epsilon rounds. We show some variations of this algorithm. First, we show how to adapt the algorithm to weighted vertex cover by bucketing the weights. And second, we show that the set S can be computed using a randomized voting scheme in log n rounds, which gives us a log n plus 1 over epsilon round algorithm in the congested clique model. Just to recap, the two main distributed results of this paper are a 1 plus epsilon approximation algorithm for G squared MVC in n over epsilon rounds and an n squared lower bound for any C approximation for C less than 9 over 8 for G squared MDS in the congest model. Let me end by stating some open problems. For vertex cover, our 1 plus epsilon approximation algorithm only works on G squared. So can we say something about G or G to the R for R greater than 2? Even getting a approximation factor slightly below 2 would be interesting here. For dominating set, can we extend the n squared lower bound for larger approximation factors? Also, studying the same question for G and general powers of G is open. This concludes my talk. Thank you for watching.